Dr. Muhammad, and this is another video regarding our seismic design of structures. I'm going to talk in this video about the configuration irregularities in ASCE. So I hope that after this video you can understand the meaning of configuration irregularities. Okay, so this part actually is an important part, and we need to understand it well so that we can understand the meaning of the irregularities that is ASCE is providing. Okay, so now let's jump into the introduction for our topic. So I'm going to start the introduction directly from the section in ASCE 716 which is relating with or dealing with the irregularities in structures. So you are going to find this section under 12.3.2 section. We have like two subsections here, and you are going to find the first subsection is dealing with the horizontal irregularity, and the second subsection is dealing with the vertical irregularity. So in irregular and regular classification, as we said, structures shall be classified as having a structural irregularity based on the criteria in this section. Okay, such classification shall be based on their structural configuration, as we are going to see. For the first type of irregularity, which is horizontal irregularity, structure that have one or more of the irregularity types listed in table 12.3-1, which is going to show to you here. This is still, we are sourcing from ASCE 716, okay, the latest edition up till now. So this is the table 12.3-1, and you are going to find, as you can see, 1A, 1B, 2, 3, 4, 5 different types of irregularities. So for the horizontal irregularity, we have 5 types of irregularity, and for the first irregularity, we have 2 subclasses. And this is the definition for each one of them. I'm going to go into the detail of it, but just I want you to see this table, okay? And you are going to find that the description of the irregularity itself in one column, and in the second column there is a reference section that is giving and describing the details of this description in the narrative or the text of the code itself. And here the seismic design category application, which means that it applies to what type of seismic design category. Okay, now this is for the first subsection, which is dealing with the horizontal irregularity. For the second subsection, okay, we are going to talk about the vertical irregularity in this section, which is going to be listed in table 12.3-2. So it's the second one here, this one. It is dealing with the vertical irregularity. Still we have 1A, 1B, and then we have 2, 3, 4, 5A, 5B. So in case of vertical irregularity, we have 5 classes, but under class A and class 5, we have 2 subclasses. Okay, so we have 2 subclasses. In a similar fashion, there is a description and reference section and the seismic design category. Okay, now this is what is written in the code, in the body of the code. Now let's go and understand each irregularity in detail and understand how this would happen. So for the planned structural irregularity, or we call it horizontal, so we can call it horizontal or plan, we have, as we said, 1 till 5. The first one, we call it torsional irregularity, which is 1A, and under 1 also there is 1B, which is extreme torsional irregularity, and 2, it is re-entrant corners, and 3, type 3 irregularity is diaphragm discontinuity, And type 4, it is out of plane offsets. And type 5 irregularity is non-parallel systems. Non-parallel systems. Okay, so we are going to go into every one of them and we are going to understand it. So for the torsional irregularity, 1A, the larger story drift more than 1.2 times the average story drift. So let's assume that we have a plan like this and we have like one drift at one corner and there is another drift on the other corner. So whenever that we are talking about 1.2, that we need one, the largest one, which is seemingly to be 2 here, it is larger than 1.2 the average of them, which is delta 1 plus delta 2 over 2. Okay, so this is the meaning of this 1.2. So if we have a kind of displacement at the corners of the building and the average of them multiplied by 1.2 is less than the largest one, then we have torsional irregularity type 1A. But if we have this factor instead of being 1.2 to be 1.4, then we are going into the second or the next level, which is 1B, extreme torsional irregularity. Large story drift more than 1.4 times average story drift, and there is a precautions here that is it is not permitted in design categories E and F. Now we can realize the importance of the design categories that we have explained in the previous video. So now in extreme torsional irregularity, not applicable for E and F. And the design forces for lateral force connections to be, for the connection, lateral force connection, to be increased by 25% in design categories D, E, and F. Okay, and D, E, and F we are going to we are talking about this extreme. It's not allowed here, but for this one it's okay. And I'm going to make like a summary here, so that you're going to understand it really easy after that. Okay, so for the first and for the first horizontal irregularities, we call it plan irregularities. This is a summary. This is a summary of what I have explained. So I put it in like 2 slides for you to understand it easily. So for the first one, torsional irregularity, we have, as we said, delta 1, which is the largest drift in one corner, one of the corners. It is going to be larger than 1.2 delta 1 plus delta 2 over 2. Okay, and for the extreme torsional irregularity, it is going to be 1.4. The factor is going to be 1.4 the average. Okay, so there is something here that is added. This is actually from Taranath book, Taranath, which is a very famous book for. Even that I have some comments on this book, but anyway, it is to some way it is good because it is listing the summaries and making it easy for us to understand. So here there is something that is important, that for example there are some, as we said, SDC application for the seismic or for this torsional irregularity with 1A. It is applicable from D through F almost for all of the categories, but we have something called remedial measures. Means that if it is going to be in the seismic design category, going to be D or E or F, then there is something that should be taken into consideration, which is, we call it remedial measure. Remedial measure, it is 1 here, it is indicated as 1, and in the next slide here, this is 1. Sorry for this. So this is 1. Let's go back and then come here. So this is 1 here. The meaning here is what? Increase design forces determined by static procedure by 25% for connection of diaphragms. So whenever that it comes to the connection of diaphragms, we need to increase it by 25%. To vertical elements, so the connection of diaphragm to vertical elements and to collectors, and for connections of collectors to the vertical elements. So whenever that we have collector or a diaphragm, their connections with the vertical elements, okay, need to be designed by an increase in the forces coming from the static procedure by 25%. Okay. Collectors and their connections also shall be designed for these increased forces unless they are designed for load combinations with overstrength factor omega. Okay, so anyway, this is the remedial measure, as we can see. And in general, it means that we are going to increase by 25%. So this is the remedial measure 1 that we should put in our mind. Okay, so let's go back. So this means that we have remedial measure 1 if it's between D, E, or F. Okay, if it's going to be between C and F, so C, D, E, F, then we need to apply also the remedial measure 2, which is going to be something here. Multiply, there is another thing that we should use. That is, we're going to multiply the torsional moment due to accidental torsion. This is something that we're going to talk about it later. Accidental torsion, it is a mandatory kind of torsion that is going to be applied on our system. Okay. By a torsional amplification, we need to have a torsional amplification factor. No need to go into the details now, just you know that there is a kind of torsional amplification is going to be used in this case. Okay, so we are going to use torsional amplification here. I'm going into these remedial measures at the end, so I do not want to bother you now with these remedial measures, just I want to give the summary now of what is the horizontal irregularities. So this is the first one, which is torsional irregularity and extreme torsional irregularity. The difference between the two, that is 1.2 here, 1.4 here. That's it. And keep this part now aside because I'm going to explain it later. Okay, now let's go to the next. Okay, now this is the next, which is type 2. We call it re-entrant corners. So re-entrant corners means that whenever that we have corners like this, this is what we call it re-entrant. Something that is a corner that is taking part of the building. The building is not symmetric, so we call this re-entrant corners, as you can see. Both projections beyond the corner are more than 15% if of the planned dimension of the structure in the same direction. So if we're going to talk about this part, for example, this is the re-entrant, so we need to measure it with this part. If this one is larger than 15% of this dimension, then type 2 horizontal irregularities apply. Okay, so if we have this is larger than 15%, if it's a small one like this one, for example, it's a small one. So in this direction, if we're going to talk about this direction, this small re-entrant compared to this direction, it is less than 15% apparently. So there is no horizontal type 2 irregularity here. Let's put it in our summary and see. So this is the re-entered corner irregularity, and this is actually how it looks like. If we have re-entrant in any direction now, so if we have B, which is in this direction, so B is going to be compared to A. B, if it's larger than 15% of A, then it is going to be type 2 horizontal irregularity. If we have D or E larger than 15% of this direction, which is C, then we are going to have this re-entrant corner irregularity. Okay, so now let's go to the detailed. Okay, so now we know about the type 2 horizontal irregularity. Let's go to the type 3, which is diaphragm discontinuities. Whenever that we have a plan, and this plan, this is considered the diaphragm, and we have a cutout here or open area, then if this open area is XY larger than 50% of the total area, then we are in trouble. We are in the type 3 diaphragm discontinuities. Okay, so that's the point. That so this is in the area itself, because it is going to decrease the stiffness of the diaphragm. Or if we have a kind of change in effective diaphragm stiffness of more than 50% from one story to the next. So if we have like different stories, okay, and we have diaphragm, this diaphragm, okay, stiffness is larger than the diaphragm stiffness here, okay. For example, if the thickness is different than the thickness, or if we have cutouts or opening in one diaphragm in one floor larger than the other, then this type of discontinuity applies. So what we're going to do in this case, the design force for lateral force connections to be increased by 25%. We're talking about connections here. In design categories D, E, and F. Okay, D, E, and F. Okay, so let's go to the next type of irregularity, which is type 4. We call it out of plane offsets. Out of plane offsets. As you can see here, this is the lateral resisting system. Okay, this is okay, no problem, because it is in the same, there is no offsets here. But the problem here that you are going to find that this is the system. However, there is like offset here, and then the lateral resisting system is moving in this, or shifted to this axis from here, from the out, or from this axis to another axis. This is what we call it out of plane offset. Out of plane offset. Okay, discontinuities in a lateral force resisting path, because here, look here, the force is moving. Actually, whenever that we are talking about structural system under earthquakes, lateral resisting system, we are highly concerned with the smooth transition of the load path from one story to another. So whenever that we have like story shear here, whenever that it goes down to be transferred or shifted or transmitted from one story to another, there is some, exactly, there are some shear forces here in this direction is going to be transmitted through the floor itself, which is something that we do not want. We need to take care of this part, which is the connecting part between the two entrants, or between the two lateral resisting system offset, or the offset, this offset. So this means that we need to take consideration for this part. This is why they said that design forces for lateral force connections to be increased by 25%. So here we need to go, if we go back here, so this means that this part, we have a connection here, right? Connection between this lateral force resisting system and the whatever the element is going to be here. Then it should be the force that is going to be designing this part should be increased by 25% if we are inside design category D, E, and F. Okay, so this is type 4 out of plane offset. Okay, out of plane offset. Okay. And type 5, we call it non-parallel systems. Non-parallel system means that, as you can see, we do not know where exactly the lateral resisting system. Okay, sometimes we can have on the other structures something similar to this, for example. Okay, so this means that it is not clear. The vertical lateral force resisting elements are not parallel to or symmetric about the major orthogonal axes of the lateral force resisting system. They are not parallel. If we're talking about some orthogonal axes, for example, like this, we cannot find where our lateral resisting system. So in this case, we need to analyze for forces applied in the direction that causes the most critical load effect for design categories C to F, C, D, E, and F. Okay, so maybe we can put the earthquake from this direction and this direction. Maybe we need to apply like 100% in both directions, as we are going to see in the remedies. Okay, so this is the fifth one. Let's summarize them. We already talked about the number 1, torsional effective torsional irregularity. Number 2, re-entrant, as you can see here. Diaphragm discontinuity, which is 50% of cut out or open area from the diaphragm, or there is a difference in the stiffness of the diaphragm from one story to another. Out of plane offset irregularity, we mentioned that it is not the same for the lateral resisting system in one story to another. Maybe we have like two columns here, we have a shear wall here, or maybe this shear wall is going to be here, for example. So this is what we call it out of plane. Okay, out of plane. And then we have non-parallel system irregularity, non-parallel system irregularity here. Okay, now let's go to the second part that I was saying that I'm going to explain about it, which is the remedies for these cases. So here, one, as we said, one always you're going to find it, one here, one. So this means that when we have D, E, or F seismic design category, this means that we need to apply this remedy, and also we need to apply this remedy, which is 5. Already we mentioned about 1 before, increase 25% for the connections, and 5 here means that use modal analysis or more rigorous procedure. So that's very important, that we cannot use lateral force or equivalent static force method. We need to use modal analysis. We need to use modal analysis. Okay, so that's the meaning of 1, and this is the meaning of 5, and 1, it means that 25 increase in the connection. Similar here, 1 and 5, it is the same exactly, so we need to use 25 increase and the connection force, design force, and 5 means that modal analysis or more rigorous analysis. We're not allowed to use the equivalent lateral force method. The same in the out plane offsets, type irregularity 4. We need to use, if it's between D and F, we need to use 25% increase, as we said, or modal analysis or more rigorous. And here, if it's B to F, we need to know what is 7 and 3. So let's go here. So for 3, we need to perform 3D dynamic analysis with the consideration for diaphragm stiffness, because it is related to the diaphragm. So we need to conduct 3D dynamic analysis considering the diaphragm stiffness. Use cracked section properties, take care, cracked section properties for concrete elements, and include P delta effects. So 3 things that we need to take into consideration: diaphragm stiffness, cracked sections, and P delta effect. So this is for 3. What about 7? 7, we need to design columns, beams, trusses, or slabs supporting discontinuous walls or frames to resist maximum axial forces determined by using the following load combination with overstrengths. Again, we're not going to go into the details of the combination. Later we can understand it, but I want you to understand the main idea here, because we are dealing with something related to the discontinuity of the lateral force resisting system. So this means that if we have a column or a beam or a truss or a slab supporting these discontinuous walls or frames, then it must be designed to resist maximum axial forces determined by using the following load combination. Okay, axial forces, take care, because go back again. What is our problem here? Yes, because if we have discontinuities, maybe the other one is better here. Yes, this part, if this is the slab, for example, here, this slab is going to transfer what? The shear coming from this part to this part of the lateral resisting system, right? This means that this beam, this slab here, needs to be designed for, exactly, for extra loading. As we said, it is going to be, yes, extra loading, including overstrength factor. Overstrength factor, as we are going to find later on, that it is going to increase the loads for the design loads for these elements. This means that we are going to make them elastic during the analysis, increasing their design forces, making them to be huge with like sufficient amount of strength, so they are not going to be into the nonlinear range, and we are going to keep them like behave elastically during the earthquake. Okay, did you understand this idea? It's very important to understand it, whether that it's a column or a beam or a truss or a slab, whatever. Overstrength factor is going to be used here to maintain these important elements to be elastic. So we are going to use overstrength parameter or factor in our design combination. Okay. Now for, okay, this is 7, and we understood now 3 and 7, 1 and 5 already we mentioned about them. And here for non-parallel system irregularity, we need to know what is 8 here. 3 and 5 already we understood. Now let's go to 8 and see what is the point here. For 8, use 100 in x direction plus 30%, okay, in y direction of the load. So if we have something like this, okay, so we need to put like 30% here and 100% here, okay. If you are using ELF, okay, or modal analysis, if we are going to use ELF, which is equivalent lateral force method, or modal analysis, we need to use this combination, okay. Use simultaneous application of load if you are analyzing the structure using linear or nonlinear response history procedure. If we're going to use linear or nonlinear response history, then we are going to put, exactly, we are going to put, say something like this, 100% here, 100% here, simultaneously, as they said. So it is more stringent. If we use ELF, then we are going to use 100% in x direction, in the main direction of the loading, and 30% in the y direction. If we're talking about this is the main direction x and this is the y direction, so we are going to use in this case it will be the opposite. So if we are going to talk about our structure here, so it is going to be like 100% here, 30% here. This is when, if we are using equivalent lateral force method or modal analysis, okay. But if we're going to use linear or nonlinear response history procedure, as we are going to understand later what is the meaning of linear response history, I have indicated it before in the previous videos. I hope that you can revisit these videos again. But anyway, this means that if you are going to use less rigorous methods, this means that you need to apply this method, this like 30, 100 and 30%. But if you're going to use nonlinear time history analysis, linear or nonlinear, then you need to be cautious and you need to use like 100% in every direction, okay, simultaneously. Okay, so now we understood what is the meaning of all of these remedies, okay. This is the mean of remedies. You're going to find something here like 6, for example. This is an extreme torsional irregularity. We mentioned that it is not allowed in seismic design category E and F, right? So this is the application of the seismic design application in E and F. Actually, 6 will nullify this. You are going to find 6 means that not permitted, NP. So let's see here. This is 6, which is not permitted, NP. So it's not allowed in these two different types of seismic design category. Okay, I hope that you understood the meaning of the horizontal irregularities in general, and what are the remedial measures that we should use, and what are the SDC applications available for them. Okay, now let's go to the second part of this video, which is related to the vertical irregularities. We have here 5 different irregularities. We have 1, 2, 3, and 4, and 5. We have 1A and 1B. Okay, and we are going to find like 2 different stiffness irregularity. We have soft story and extreme soft story. Okay, so we're going to find 1A and 1B. I guess that we are having, if we look to the summary here, So we are going to find that also for 5 we have 5A and 5B, which is weak story and extreme weak story. So I think that here we need to be a little bit more accurate. So here we have weak story, this is 5, but this weak story is going to be 5A and we have 5B. So this is weak story and this is extreme, okay, extreme weak story. And remember, we are going to give summary for this in an easy way, so don't worry, you are going to find everything written in the summary. Okay, let's go to the first one, which is the soft story. We have 1A and 1B. We have soft story, which means that it is related to stiffness. Take care, this is related to the stiffness. The lateral stiffness is less than 70% of that in the story above, or less than 80% of the average stiffness of the 3-story above. So that's the case here. If we have one story that its displacement, okay, if we're going to talk about stiffness means that it is the reciprocal of the drift. So this is why we said that 1 over delta should be less than 0.7 of 1 over delta 2 if we're talking about delta 1 and delta 2. Okay, so this is delta 1 here and this is delta 2. This is delta 1, I guess. This is delta 2. In the summary, I think that it's better written in a better way. So here, stiffness irregularity, which is soft story. Our criteria is the stiffness, that A should be less than 70% of B. So the stiffness here at this story, which is story A, should be less than 70% of the stiffness of story B. Or A is less than 80% of the average stiffness of the 3 stories above. We have B, C, and D. So this is the definition of the story, of the soft story. Stiffness irregularity for extreme soft story, which is 1B, it is going to be the same values, the same idea, but with the values is a little bit less, which is 60% and 70%. 60% and 70%. This is extreme. This means that extreme case. For vertical irregularity number 2, the mass is larger than 150%. So if we have mass here for B, for example, larger than the mass of A by 50%, this means that we have weight or mass irregularity. Okay. And then if we have vertical geometric irregularity, which is having something like this, that we have Y, this is the mean lateral resisting system. It starts with length X and ends at the top with length Y. This means that the dimension X here is larger than 130%, okay, of Y. This means that we are having vertical irregularity in type 3. Okay, so we can go here. Vertical geometry irregularity. Commonly it is going to be something like this. That we have 2 columns here, or we have something like this. So this is the vertical geometry irregularity. Okay. Now for 4, which is in-plane discontinuity in vertical lateral force resisting elements. That is in plane, means that in the same plane, instead of having, this is the shear wall, we have a shear wall here, and we have the shear wall in the second story is shifted like this. So this means that an in-plane offset of the lateral force, in plane means that they are in the same plane, but there is shift in it. It is different than the horizontal irregularity that we mentioned before, offset in the lateral resisting system. In the horizontal, it was in the plane itself, there was shifting in the lateral force resisting system. Okay, so the lateral force resisting system, there is kind of shift. This is in the first story and this is in the second story, so there is a horizontal here. This is what we call it out of plane, but here we call it in plane. This is in the same plane, okay, but it is shifted. The shear wall is shifted. Okay, this is shifted from here to here. Okay, design forces for lateral force connections to be increased as well, as we said, 25% in design category D, E, and F. We're going to check this, okay, in the remedial measures at the summary. And the last one is the discontinuity for the weak story. For the weak story, let's see it from here better. So for the weak story, we have two types, which is 5A and 5B. This is weak story and this is extreme weak story. We have weak story and extreme weak story. If the shear strength, we're talking here about shear strength, it's not stiffness. Take care, it is shear strength, not stiffness. If the shear strength of story A is smaller than 80% of the shear strength of story B, as you can see, then it is weak story. But if this shear strength here is less than 65%, then it is extreme weak story. It is extreme weak story. Okay, so let's go now to the remedial measures that we need to understand what is going to be done. We understand now that, for example, 6 here is very, very unique for us because 6 means not permitted, as we said before. So it is not permitted in E and F. This extreme soft story, not permitted in E and F SDC. And then the remaining here is 5, 5, 5. We remember what is 5. Let's recall it here. This is 5. Use modal analysis or more rigorous procedures. So equivalent lateral force method is not allowed here. So let's go back. So this means that here it's not allowed for the soft story and for extreme soft story and for the mass irregularity to use equivalent lateral force system. It's not allowed. We need to use modal analysis or more rigorous, which is non-linear time history analysis or linear response history analysis. Okay, so this is for vertical irregularity 1 and 2. Let's go to the 3 and 4. As you can see, it is still 5 here. 5 here means that modal analysis or more rigorous. And we have 1, 1, it is not permitted. So it is not permitted in D and F. This type of irregularity is not permitted in D and F. Okay, D through F. And let's go to the next, okay, the next one here, which is the vertical irregularity type 5A and 5B. As we said, 5 here means that more rigorous or modal analysis. 6, it's not permitted. Okay, and we said that 9, let's check 9. What is the meaning of 9? Maximum height limit, which is 30 feet or 2 stories, unless the weak story is capable of resisting a seismic force equals to the overstrength factor parameter times the design force. So this means that we need to limit the height here. This needs that extreme weak story we need to limit the height of it. Okay, so this is actually what we are going to. This is the summary of all the all of the vertical irregularities. I hope that you understand it well, and next time we're going to talk about the examples, some examples for what we have explained today, so that you can understand the idea very well. Okay, thank you, and see you in the next videos.